Hello, good people. Welcome to video one of topics 3.4 and 3.6. These are actually the last of the derivative rule videos, or I guess formulas that we need to know. And then after this unit three, we get into the application of it. So we're going to continue to practice and do these rules over and over and over again, but we'll be doing it in a context of some application problems like motion, like related rates, like all these different types of situations where we're going to need to find derivatives, but we will have practiced them over and over again to keep doing these rules so that they stay in your head. Okay, so the first part of this video series is talking about how to find a derivative of an inverse trig function. Now, just to recap, an inverse trig function would be like sine inverse, right? Tangent inverse, secant inverse. And so what you need to remember, and I guess I'll write it right here. Let's say that we have, for example, y equals sine inverse of x. So what do sine inverse functions do? Or what do trig inverse functions do? Well, the purpose of trig inverse functions is to find angles. So when I do sine inverse of x, I'm giving you the answer. I'm giving you the ratio, the trig ratio, and I'm asking you what was the angle that produced it. So I need you to realize that this is the ratio. And when I say ratio, I mean like square root of 3 over 2, or 1 over 2, or square root of 2 over 2. I'm giving you the answer. And what I'm asking for is what is the angle at which that ratio happened. So usually I tell you find the sine of pi over 6. And the sine of pi over 6 would be 1/2. Well, with the sine inverse, I'm asking you what's sine inverse of 1/2? Well, one of the angles is pi over 6, but there could be more, right? Because we have multiple possible angles where we get that sine ratio. And so the very first thing we need to remember is whenever we're dealing with a sine inverse equation, we can always rewrite it as the sine, let me use a different color here. The sine of the angle is equal to the ratio. This is normally how we see it, right? The sine of an angle is equal to some kind of trig ratio, one of the coordinates on the unit circle. Sine inverse says, give me the input as a ratio, I'll spit out the angle. But if I rewrite it, what I've really done is I've created the inverse function. So this is the inverse function. We're now going to take the derivative of the inverse function, and we're going to take the derivative implicitly. So we're going to find d dx of this side and d dx of the other side. So we're going to take the derivative with respect to x of x and of sine y. Well, when we take the derivative of x, we get 1. And when we take the derivative of sine y, well, we get cosine y times the derivative of the inside, which would be dy over dx. And so now I know that dy dx is 1 over the cosine of y. Now, when I look at this, this becomes an interesting exercise because if you recall, we said whenever we're taking the derivative of an inverse, and this is just any generic inverse, which is what the previous unit was about. Whenever we're taking the derivative of an inverse, take the derivative of the original function. So if sine inverse is my inverse function, then the original function is sine. So take the derivative of sine, and my inverse is going to be 1 over cosine, 1 over the derivative of the original function, which is what I have right here. The derivative of y, which is the derivative of the inverse of sine, is 1 over cosine of y. Why? Because cosine is the derivative of the original function, not the inverse, right? And so here I have my derivative formula. Except, well, everything is in terms of y. And I would like it to be in terms of x. And so if I come over here, you'll notice that they drew this triangle for me. And the reason they drew it for me is because they want to remind me that sine of an angle is really the opposite over the hypotenuse. So if my sine of y is x, it's really x over 1. So if this is angle y, this would be the opposite side, and this would be the hypotenuse. So I could label a triangle with this equation. With the information from that equation, I could label a triangle. Not only that, using the Pythagorean theorem, I can figure out this side of the right triangle. And so I would say the side that I'm missing squared plus the other leg squared equals the hypotenuse squared. Or you could say the question mark squared, this one that I'm missing, is 1 minus x squared. Or you can say the question mark is actually just the square root of 1 minus x squared. Remember, whenever we take the square root, it's usually positive or negative. But since we're talking about the length of a triangle here, I'm going to say it's positive square root of 1 minus x squared. And so here, I just figured out the length of this triangle. And at the beginning, you're thinking, what does this little trig side work have anything to do with it? Well, we were able to use this information to label a triangle and figure out the third side. Because if I want to convert cosine y in terms of x, this triangle can help me. Because if you recall, cosine y is adjacent. I'm looking for cosine y here. Cosine y is adjacent over hypotenuse, which would just be square root of 1 minus x squared. Because square root of 1 minus x squared divided by 1 is square root of 1 minus x squared. So therefore, I can come back over here and say, oh, when we were looking for the derivative, this was the derivative, but it's in terms of y. But I can also write that derivative in terms of x because now I know that cosine y is the square root of 1 minus x squared. How do we figure that out? Oh, by drawing a triangle. How did I label the triangle? By this piece of information, this equation that we started with that told us the sine of y is the opposite over the hypotenuse. I was able to label the triangle, find the third side, and figure out that cosine is this. And so some people say this is the derivative of sine inverse. Now remember, we're finding the derivative of y with respect to x. The derivative of y is the derivative of sine inverse. So what we're saying is the derivative of sine inverse is either 1 over cosine y, or it's 1 over the square root of 1 minus x squared. And a lot of people choose the second one because it is in terms of x, which is what the original y equation was in terms of. It was sine inverse of x. And so when I look at my table, that's exactly what I see here. This says, if you're taking the derivative of sine inverse of something, well, then it's 1 over the square root of 1 minus the something squared times the derivative of the something, which is why there's a u prime there. So they're basically applying the chain rule to those. So what we have in this table is all of our derivative formulas for the inverse trig functions, like sine inverse, tangent inverse, secant inverse. But just as before, I want you to notice that there's a pattern. When I look for sine inverse, this is what you need to remember, because the derivative of cosine inverse is the same thing, except there's a negative. And when you remember or memorize the derivative formula for tangent inverse, this is the formula, because when I'm talking about the derivative cotangent inverse, it's the same thing, except there's a negative. And then finally, similarly, I guess I should say, for secant, this is the same secant formula for cosecant, except there's a negative. So if you memorize everything in the blue columns, the ones in the green columns are similar setups, except they're all negative. They're all opposites. And that's how we figure that out. In the next video, we'll talk about how we use these formulas to figure out derivatives of inverse trig functions. But the big idea is with implicit differentiation, which is what I had to do here in green, we're able to find the derivative of inverse functions and find patterns for sine inverse, tangent inverse, secant inverse, and their co-function buddies in the green columns.